Welcome back to the Atari ST Nostalgia GFA Basic tour. In the previous video we played around with drawing graphics some more and we learned about using arrays in the process, so it turned out to be quite useful. In this video I want to take a short look back at some basics of some mathematical operators that we can use on variables and how they can work to our benefit. And I talked about them a little bit in our video about improving the performance of our spirograph in part 23b. But I decided to do a separate short video to actually explain the commands and to show the specific performance difference they can make, and then also show some clever use of some of the commands that I was reminded of through a comment in one of my previous videos. So let's go into the screen, into the editor, and as you see I'm in direct mode and I did some preparations. So I said I made this variable x with the value of 10, I printed it, so it turned out to be 10. And then I used the formula x equals x plus 1 and then printed it again to confirm that actually yes, x was increased by 1. And whenever some people post somewhere in a forum about the GFA Basic code and this x equals x plus 1 is in there, they tend to get a bit like angry reactions of people saying, oh man, you're using the wrong command and it's killing your performance. And my first reaction, to be honest, is like, come on, relax, dude. This was not what their question was about. And if they are beginners, just answer the question first and maybe suggest that you can also help them improve the code performance by using different commands. And that's what I'm actually going to do in the video, because instead of saying x equals x plus 1, there's actually a specific command in GFA Basic. It means incx, which means increase x. And increase x, as you can see, it increased it. The inc command basically increases the value of x with 1, and this command is faster than x equals x plus 1. So people who get angry about this performance degrading code, they have a point, and therefore I'm making this video to show the performance difference, so to see just how much difference it makes. And I have a little bit of code to do some measurements, and basically I'm showing that it makes sense to use the inc command, and inc followed by a variable basically means this variable, this numeric variable, increase it by 1 and use that one instead of x equals x plus 1. And the same goes if you, instead of using x equals x minus 1, there's a command called dec, means it's short for decrease. And of course there's a command called add, so instead of x equals x plus 5 you should use x add x comma 5. And the add command, basically, it does the operation on the first variable that you name. And the second one after the comma can be a constant, like I just filled in a number here, but this can also be another variable. So if I want to add the value of a second variable to the value of x, this is the command to use. You can also use sub, which is subtract, but I'm not using it in that code. And of course for multiplications and divisions, there's the same kind of commands. It's mul and diff. So this command multiplies x by 2 and it's faster than x equals x times 2, and the diff does the same. So instead of x equals x divided by 2, just say diff x2. And I've created this code to demonstrate this. So I'm going to use the timer command to get a timestamp before and after every time I do it. And I'm first going to get a baseline, just empty, do this empty for next loop. So basically I'm doing a for next 10,000 times in total. And I'll be using integer long variables for all of the calculations, because some of them create a number that's bigger than 32,000. So I use the same variable type for every calculation. So basically I will measure the empty for next loop. Then I will measure the for next loop including the x equals x plus 1. I will time that, and so I will print the total time. And I will also deduct the base time for the empty for next loop for every step that I take, to see what just the added time was for just these calculations. So I will compare x equals x plus 1 to inc x, as you can see, and I will do the same minus 1 compared to decrease x, and then I will do x equals x plus 5 compared to add x5. Yeah, and I will do the multiplication, so just the formula and then the mul command, and then the formula for division and the div command. Now the timer, using the timer command, it means the time I measure is up to 0.005 seconds accurate. The measurements might deviate a little bit by a few hundredths of a second for the same command, so the actual measurements are, but they're still accurate enough to show the difference between the commands. So let's go into the one, and the empty for next loop took like 0.26 of a second, about a quarter second for 10,000 times. which is actually quite fast, especially for a computer from 1986. So apparently the ST was actually quite a nice machine to have. So if I calculate x equals x plus 1, you can see that it took almost 2 seconds. So almost 1.7 seconds to do this x equals x plus 1 10,000 times. So how much difference will it make if I use incx, which basically produces exactly the same result, but it's a different command? Well, as you can see, it makes a lot of difference. This was like 0.22 of a second, which is like this command is 7 to 8 times faster than the previous one. So when you're using like the x equals x plus 1, if it's just a single command, you might not see the difference. But if you use it in like long loops, you can see that actually the performance difference becomes quite huge. So there is a good, yeah, it really pays to use these commands. And of course the same goes for x equals x minus 1, which takes about the same time. You can see now it took almost a tenth of a second longer even. And the decrease x is still, yeah, 0.22 of a second. Like, so also this one is like 8 times faster. And of course the x plus 5, the calculation takes about the same as the x equals x plus 1. It was a little bit faster this time, like 200ths. And the add command is not as fast as the inc command. But you can see still it was only half a second, so it was still 3 times as fast. So if you increase by 1, it's actually better to use the inc command. And if you increase by 2, it might be better to use 2 inc commands instead of 1 add command, but that's something you have to test in your code, because it will be an extra line of code, but the command itself is then still faster. So if I do multiplications, as you can see, the total net time of this multiplication was 2.06 seconds. And if I use the mul command, yeah, it still takes some time, but it's still 2 times as fast. So the differences are actually quite huge for these built-in mathematical calculations. And yeah, if you do the x divided by 2, net time was like 1.26 seconds. And if I use the div command, it's like 0.6, so also 2 times as fast. And of course, this is all running from the interpreter. And I think the performance difference becomes even bigger when you actually compile your program. If you use proper coding, like performance coding in your original code, when compiling it, there will be more performance benefits from compiling than when you don't do it. And I might get to that in a future video. I will do a short one about the compiler to show these differences. And I might do this one and the spirograph one to show you the difference in the extra benefit that the compiler will give you for this kind of calculations. But yeah, that was one thing I wanted to show. Just to show and tell works better than just complaining to people, I think. And you can see that the performance differences for these commands is actually quite big. Now there are 2 commands that I want to discuss separately, which are the div and mod command, because you can also use them for calculations. And as you can see, first I just made a printout. Basically, what I'm going to do, I'm going to count from 0 to 20, and for every number I'm going to print the number, then the number divided by 10 using the div command, and then the number mod 10. And it's easy to show, and as you can see, what it does is if my number is 0, they are both 0, and if the number is 1, I div 10 stays 0, and the remainder is 1. So the mod calculates the remainder, and the div, basically the number div 10 means give me the maximum amount, the maximum times I can fit 10 as a whole number inside number I. So as you can see, when I becomes 10, the I div 10 becomes 1. And of course, if it's 11, this is still 1. So I can still fit the number 10 only one time in the number 11. And then I have a remainder of 1. So it's like I fit 10 once, and then there's 1 remaining. And of course, if I increase it to 12, you can see it becomes 2 again. And the interesting thing about this is, I mean, this is basically preschool or primary school calculation. So we should be comfortable with this dividing and remainder stuff. But the nice thing is that you can see this is actually a very fixed pattern that it follows. So when I becomes 10, the div becomes 1. When I becomes 20, the div becomes 2. And every time that happens, this one increases. You can see this number actually goes back to 0. And that is something we can use to our benefit to actually, we can use the outcome of the div and mod calculations as input for repeating patterns. And that was the thing I was reminded of in a video that I totally forgot about, but it actually can make your code very, very efficient. So I created some simple examples first. Basically what I'm going to do, I'm going to count from 0 to 39 in this case. And for every I step, I'm going to print the number, and I'm going to use the outcome of the diff and mod commands to as input for the print add command. So basically what I'm doing here, I'm doing I div 10, which means the x coordinate will only increase. I mean, I will start at 1, but it will only increase when I reaches 10. So every time I reaches 10, it will actually increase. And if I becomes 20, this will increase again. This number will become 2. So the coordinate will be 1 plus 2 times 10, so 21. And of course the remainder means every time for every increase of I, the y coordinate in this case, so the row number will increase by 1, except when I reaches 10, then the row number will go back to the beginning. And that will sort of show you the repeating pattern. And of course I can do the same horizontal. Instead of using the diff, I will use the mod, so the remainder for the x coordinate. And so every time I increases, it will actually shift four characters to the right. And of course, as soon as I reaches 10, it will go back to the beginning again, so to the first column, and it will only go to a new row. It will go to a new, it will only go to a new row, if I reaches 10. So this coordinate goes back to, this coordinate goes back to 0, and this coordinate will shift when it reaches a certain number. And I'm just going to show you the thing. So as you can see, this is the first one that we showed, and here you can see that is happening. So I increases to 9. As soon as I reaches 10, it means the x coordinate shifted because this div 10 reaches the number 1. And of course, because the remainder is back to 0, it goes back to the top, and it repeats that pattern all the time. And the other way around, you can see that the x coordinates keep shifting because the remainder keeps increasing until I reaches 10, which means the row number actually increases, and because the remainder becomes 0, the column number goes back to 0. So yeah, and I just use multiples of 10 in this time. You can use different numbers. For instance, if I instead of div 10, I use, let's say, div 8. It will make, instead of 4 columns of 10, it will make 5 columns of 8. And if I here do, let's say, 12, or let's do 15. And here also 15. I mean, I know I'm over-explaining this maybe, but it's good to just show and tell what happens. Now you can see, instead of having columns of 10, I have columns of 8 because I changed the command div 8. You can see that it goes back earlier, and it also shifts earlier. And in this case also, I made the rows longer. So instead of 10, it has now 15 characters per row. And as you can see, you don't have to be exact about. This doesn't have to be in ending here in the last row. It just counts, and it will apply the formula. So it doesn't really matter what you do. And of course, you can use that for printing the characters on screen, which is the formula, which actually I was doing the video about printing the characters, which contained one, and I was using two embedded for next loop to do the row and column separately. But it's much more efficient to use the div commands. In this case, 24, because I want 24 characters per column. And I will just count to 255, and it will just do it until it reaches 255. So I also don't need like if-then statements to stop printing at 255. This is just a count. And because it's one line, it's 2 lines of code less, or like even 3, because I also don't need this if-then statement. And fewer lines of code means more performance in your code. So this is the simple command to print all the characters. And of course, the cool thing is I cannot just use it for printing characters. I can actually use it to draw some graphics. So what I did here is I did the same count, but now I'm using the div and mod commands to actually draw a circle and then put some text inside it. And it makes it a bit more complicated, but as you can see, I'm doing it row by row. So I'm using the remainder here. And and after 8, when it reaches 8, it should go to the next row, which means I will have 5 rows of 8 circles in total, so 40 circles in screen. And here also, and I had to do a little bit of these. So these plus 40, this is because of the radius of the circle, because it used the center, and this plus 10 and plus 52 was basically also a bit of trying out to get the text in the middle of the circle. Yeah, and it's interesting that you can use these very simple lines for as input for, in this case, graphics commands to draw stuff. As long as you know your pattern is repetitive, it's very efficient to use these diff and mod commands. And yeah, I'm going to remove these because I just want to show the last one. So this printing of the characters, yeah, as you can see, it looks a bit the same as if you're doing the embedded for next statements like I did in the previous video. I didn't do any measurements of how much difference in performance this makes, but this looks a little bit faster. But yeah, I didn't have the timer running, and of course I can do the same with the circles, which is pretty cool. I have the command for drawing the circle only once, and the coordinates are changed based on the diff and mod commands, which are based on the increasing of I. So I found that pretty cool. Of course, yeah, this is the last thing I want to show about the commands. But the interesting thing is with text, this is quite fast. But actually, when I draw these circles, for instance, if I wanted to generate a background pattern like this is a nice way to do it. But I must be honest, this is still it looks a bit slow. I'm not really happy with the performance. So in the next video, I want to look at how we can make this drawing of circles a bit faster. And we will learn the stuff we learned in this video and some previous videos for these repetitive patterns. But instead of drawing them, there must be some other method to make it faster. I'm not going to show it here. I will be showing it in the next video. For now, I hope you enjoyed this one. We learned about yeah, the mathematical operations, how we can use them to our benefit to increase performance, and how we can also use them to our benefits to actually put repetitive patterns on screen in a very, very fast and efficient way. And with that, I would like to thank you for watching, and I hope to see you next time.